welcome to episode number 3 of CS350 Online. I'm your host, Leslie. And on today's episode, we're going to continue our discussion of threads. And in particular, we're going to look at how you can have multiple threads running on a computer with a single CPU, but still create that illusion that all those things are running at the same time. But before we get into that topic, let's look at our OS of the day. All right. Our OS of the day is called Exec1, and this operating system was released in 1962, and it was run on the UNIVAC 1107 machine, which you see pictured on the slide here. Now, this operating system wasn't much more than the operating system we discussed in our last episode. It was primarily a batch processor, but unlike the previous operating system, GMNNA-IO, this operating system offered multi-programming. And if you don't remember what multi-programming is, that's the ability to have another job run while the first job is doing an I/O operation. Remember that I/O operations used to take very long periods of time, and we didn't want our CPUs to be idle for any reason whatsoever, and hence multi-programming came to be. So that's Exec1. Now, a couple of other interesting things about this particular system and this operating system. One of the reasons why this was a particularly popular OS at the time, and popular is a really strange term for something where there was, less than 100 of these machines in the world. It had an optimized Fortran 4 compiler. That's a pretty big deal. It had an assembler that had lots of useful macros in it. It also had a very flexible linker and loader, which was a pretty big deal at the time. Now, one other interesting thing about the UNIVAC system was that when we think about how big our words are, we think of them as being in powers of 2. So, for example, if you go back into the late 80s, early 90s, our word size was 16 bits for consumer hardware and consumer operating systems. But, and then throughout the mid to late 90s, early 2000s, our word size was 32 bits. And of course, now our word size is 64 bits, and all of those numbers being powers of 2. However, on the UNIVAC 1107 with Exec1, word size was 36 bits. And the system that they were running on, this 1107, could store about 65,000 of them. So in total, this giant room-sized machine had only about 288 kilobytes of memory. It's not a lot. Most of the time, we can't even take a photo these days that's that small. All right. So where did we leave off? So in our last episode, we introduced the concept of threads. Remember that a thread is just a sequence of instructions, and threads belong to a process. And the process is the execution environment that's created for a program to run in. In order for a process to actually be able to execute something, it actually has to have at least one thread. Because if it didn't have a thread, then it wouldn't have a sequence of instructions, and therefore it couldn't actually run anything. Now, threads, there are various APIs that you can use to create them. OS 161 has a very simple API where you can call thread fork to create a thread, a new thread. Let's bring it up here. There's our API right there. So thread fork is going to create a new thread, and that new thread that you create, if you set the second argument of the fork function to be null, or to be the process's ID, it will attach the new thread to the process that you specify. And then to create that new thread's sequence of instructions, you're going to use the function pointer argument to point it towards the address of a sequence of instructions. Now, a few other things to recall about threads. When you create a thread, you are actually in the operating system creating a structure. And that structure will get attached to the process's thread array. That structure has things like a name, although that shouldn't be used to uniquely identify a thread because there's no guarantees on the uniqueness of thread names. And it has things like a pointer to its stack, and a state, like is this a running thread or a pause thread, or so on and so forth. So when you actually call thread fork, you are actually creating a new thread structure. That new thread structure is going to be attached to a process's thread array. And then what's going to happen is your new thread is going to get pushed into a pool of threads which are ready to run but not currently running. And we're going to deal with some of that discussion later today. We also have thread exit, which is going to terminate the calling thread immediately, and thread yield, which is going to say, if this thread is running currently, calling yield will cause you to voluntarily give up the CPU. Now, it's no guarantee. There is entirely the possibility that you call yield and you continue running. But probabilistically speaking, especially on a modern computer, if you call thread yield, you're probably going to be voluntarily giving up the CPU. If you need to guarantee that you give up the CPU, there are other ways that you should be doing it other than yield. So that's the API that we introduced. This API only exists inside of OS 161, and if you want to do any kind of threading in your home, you need to look into proper threading libraries. The two libraries that I highly recommend are POSIX threads, also known as pthreads, which is cross-platform, and then of course there's OpenMP, which is another cross-platform library, and both of them are very much standard. And you should get, in my opinion, threads are very important to understand, and it doesn't matter what area of computer science you find yourself in. We are always looking to improve performance and improve utilization of resources. So I would get some experience with those threading libraries. And if you want to get even more, of course, take 343, which is the concurrency course. All right, so that's where we left off last class. What I would like to do now is look at a sample problem. So you'll notice on Piazza that I have made a post about extra sample problems and guides. And there's not much posted in that right now. I'll be filling that in over the course of this week with a bunch of guides, sample problem things, a whole bunch of extra content to help you understand what we're going to be talking about and to help you through assignments and so on and so forth. Part of that, and if we were doing this course in person, we would do actual physical handouts where we hand out a piece of paper with a sample problem on them, and we give you time in class to actually do this. Now, obviously, I can't physically hand you a sheet of paper right now because many of you are located around the world, but I still want to do those problems because I think it's really good experience, and it will help you judge whether you are understanding them or not. So on that sample problem thread, you'll actually see a zip file called handouts, and in it, you can actually just open it up here. Here's my Piazza. There it is. So if you go into extra sample problems, you'll see here handouts.zip. That's the one you want. And in there, you will see one called fork print, and that's the one that we're going to do right now. So fork print is going to, you'll see this helper function here, and it is going to call thread fork twice. So if I, the integer we pass into helper, is less than 3, we are going to print our integer num, that I, and then we are going to do 2 forks. And each time we fork, we're passing in I plus 1. And then if I is equal to 0, we are going to print out 0 again. And then once the thread is done its work, we're going to call exit. Well, this here is kind of redundant because when you reach the end of the sequence of instructions and you return, it's going to terminate the thread anyways. All right. So the question we have is based on this little snippet of code. Which of these different outputs are possible by this program and which ones are not? Now, this is a tricky thing. And it's tricky because you have to ask yourself, how does this code behave? what is impossible and what is possible. And some people have a really hard time, especially when you're new to threads, trying to figure this out. And I want to tell you that there is some magical mechanism you can use to solve this, except there really isn't. And my recommendation to you is to actually try drawing things out as like a thread tree. So like here's your original thread, and then you call fork, and now you've got 2 threads, and then this one calls fork, and now it's got this. So that's something that you can do, but that's not going to give you the answer. A couple things to remember otherwise when doing problems like this. One is that you have absolutely no control over what order threads will actually execute in. When you fork a new thread, you might be thinking that thread is going to start running, but there's no guarantee of that. The thread typically gets created, that is, the structure is produced, and then the structure is going to get added, or at least a pointer to the structure will get added to a ready pool. But that doesn't mean it's going to start running right now, because some other thread could be running. And that doesn't mean when the thread that's running right now is done that your new thread will run either. There may be other threads with higher priorities, or who knows, that are going to run before your new thread. So when you call thread fork, there's no guarantee that the thread is actually going to immediately run. You have no control over when these threads run. The other thing to keep in mind is, even though typically when we do an I/O operation like printing, that would typically cause us to run another thread in this multi-programming style, but it's not a guarantee, so it may or may not happen. But those are just some things to keep in mind as we work through this. So I'm going to open up OneNote here so I can actually write. Let's actually look at this. So our first one here is 01221220. And I'm going to tell you that the first one is a yes. It's possible. One of the things you'll observe by looking at this is that we print our number before we fork threads. So what that's saying is, if we are the 0th thread, we actually are going to print before we fork anything. And that is actually going to happen. So all of these should start with the 0. The other thing that this is telling us is, because we print before we fork, and we fork twice with a higher number, that for each number, say number 1 or number I should appear before 2 I plus 1s. That should always be the case. So if you see 1 followed by 3 2s, that doesn't make sense, because we only spawned 2 new threads for each thread numbered 1. So how would you get the third one? So keep that in mind. So the first one is definitely possible. The second one is also possible. So you'll see that we are printing before we fork, and you'll see that each 1 is followed by 2 2s. Now, the one thing you might be confused about is this second 0 here, which is the first thread, the 0th thread, is going to print before it forks, and it's going to print after it forks. And you might be thinking that you have to wait until all of the other threads have finished before you get to print that second 0, and that's simply not the case. You may start, print your 0, fork off your 2 threads, and print your final 0 before the other 2 threads ever run. So you can even have things go 0 0. That's totally possible. Now, C is a no. The reason why C is a no is because we have this restriction here. We only fork off a new thread if I is less than 3. So when we create 2 threads whose value for I is 3, we won't enter this branch. We won't print our numbers. We'll just terminate immediately. So you can't have any number printed out that is greater than or equal to 3. That's all there is to it. D, this one is also a no. And the reason why D is a no is because we have 1 1 followed by 3 2s. And each thread labeled 1 can only fork 2 threads labeled 2. And since the other thread labeled 1 hasn't printed yet. That means it hasn't forked yet either. So this one is also impossible. E is totally possible. F is impossible, again, because we have numbers which are greater than or equal to 3. And then G is possible. And of course, H is also possible. So there you go. We have worked through our first problem. Now, this isn't how I'm going to typically do things in future episodes. What I'm probably going to do in future episodes is I will introduce the problem to you in episode I, and then in episode I+1, we will take up the solution to it. And that will give you an opportunity to try the problem on your own. Now, one of the things I want to say about these sample problems that we typically do in class is that these are actually previous midterm problems, like actual real midterm problems. And if you want to get a lot more experience with the content in this course or test whether you're understanding things, go to our course website and hope it loads. Of course, it would be my luck that the CS server isn't loading today. But go to the CS server, go to our website, and on our website, what you're going to see is that we actually have some, under our discussion of exams, we actually have a lot of sample problems, and in particular, all of our previous midterms from almost like 2003 up till very recently with their solutions have been posted to the course website. So you have lots and lots of sample content to use to help you check if you understand the material or not. All right. So let's get back to talking about threads then. There we go. All right. So we've talked about how the threads are created, and we've talked about how they are sequences of instructions. But how do you actually run or implement concurrent threads? That is, threads that either are truly running in parallel, that is executing instructions at the exact same time, or at least giving the user the illusion that those threads are running in parallel. That is, well, it appears that I have 10 Chrome tabs, and it appears that they are all running at the same time, but in reality they aren't. How do you do this? How do you implement this? Well, there are a few different options that we have. The easiest option, and the option that we're not going to go into any great detail, is this concept of hardware support. So if our hardware, we may have multiple processors. That's not so common in today's desktops, but it was pretty common in the 90s and the early 2000s. You may have multiple processors. Each of those processors may have multiple cores, and each of those cores may support some degree of multi-threading. And if you actually have any of those things, then you can actually execute some number of instructions actually at the same time, truly in parallel. And the total number of threads that you can execute in parallel is actually equal to those three numbers multiplied together. So if you have one CPU, that's one processor, and that one CPU has 10 cores, and each of those cores has 2 threads, then you have your degree of multi-threading support is going to be 20. So you can support 20 threads truly running in parallel. My laptop here that I'm using to run these episodes is a Core i9. It has 6 cores, and each core has a degree of multi-threading equal to 2. So I can run 12 in parallel. All right, so a quick question on Twitch here. Students are asking, isn't it possible that it takes a really long time for one of those numbers to print out? Yes, but things like printing to the screen have a tendency to be a blocking operation, which would prevent the thread from actually executing the thread fork until the function printf had returned. That comes down to how is printf actually implemented. All right, so hardware support, that will give us 12 threads on my machine. But if we actually look at my computer here, and let's go over here, and I'm going to open a program called top, which is a standard Unix command. And what you can see here is that I have 515 processes in total. And of those 515 processes, between them, I have 2,818, well, it's constantly changing here, threads. Okay, so I can only run 12 threads in parallel, but I have over 2,800 threads actually on my system in existence right now. How do we do that? That's actually where the interesting bits come into play. So what we're going to do is we have a fixed number of hardware resources to actually physically run the threads on. So we need some way of giving the illusion of all of those threads actually using the CPU at the same time. And how we do that is by rapidly switching between threads. So thread A gets a short period of time, and then thread B, and then thread C, and then we're gonna rapidly switch between them. So in a minute, no one thread gets the whole minute to run instructions, but like 100 threads will get a little bit of time. So all of those programs will make some progress. And we do this at a fast enough rate that it gives the illusion to the user that those programs are actually truly executing at the same time. And this is called time sharing. And another way to think about this is timeshares, as in a vacation house, famous South Park episode. I didn't actually know timeshare real estate was a thing, but there it is. The idea is you can't afford a vacation house, but you and 19 of your friends, or maybe 19 random people off Reddit, you get together and you buy a vacation house together. And since you've each paid 1/20th of the cost, it makes sense that you each get 1/20th of the time to use it. So you are time sharing your real estate. And that's exactly what we're going to be doing with the threads. If there are 100 threads, then each of those 100 threads should get 100th of the CPU's time. So we're going to time share. Now, in reality, because we do have, since about 2003 roughly, we have at least had the ability to run 2 threads at the same time. We actually do a combination of both hardware support and time sharing. So my computer right now is actually doing both time sharing and actually running threads in parallel. And if you are running on Windows, you can actually open the task manager up, and it will actually show you, a little plot for each of the CPUs, and you can see, or each of the cores, and it will show you how much is running there. It's kind of neat. All right. And I'm sorry to the Twitch user who almost got scammed by timeshare in Mexico. Be careful of these things. I honestly didn't know that was a real thing. I thought that was just something South Park made up, but no, it is a real thing. And if you haven't seen the episode, go watch it. All right. So we're not going to talk anymore about hardware support, actually. And the reason for that is it's not interesting. It's just not. We're going to talk only about time sharing. So with time sharing, as I said, you're going to be rapidly switching between threads. And we actually have a name for this process of switching from one thread running to another thread running, and we call it a context switch. Your CPU only has one, or your core only has one set of registers. And while a thread is running, those registers are going to contain the values that pertain to the running thread. So the program counter will be an address with thread A. The, register 31 will be the return address, and so on and so forth for thread A. That is a state or a context. And when we want to switch from one thread running to another thread running, we need to change the state. We need to change the context. I need to change the CPU's register values from being thread A's registers to the register values that I would expect to continue executing thread B. Now, what happens during a context switch? Actually, a lot of things. It's not just the register swapping that's going to happen here. What's actually going to happen is that first, when we register the fact that we want to perform a context switch, that is, we want to switch between two different threads, I need to find which thread I'm going to go next. There's lots of reasons why thread A may decide it doesn't want to run anymore. One such reason is that thread is dead because it called exit. Well, we don't want to waste the CPU's resources, so we want to make sure that when a thread terminates, then a new thread is going to run. If a thread calls thread yield, then we are voluntarily giving up the CPU, which means we are volunteering for a context switch. And there are other reasons that we may do this as well. So when we are saying, let's do a context switch, we actually need to choose another thread to go next. And how we choose which thread goes next is the topic of scheduling, and we're actually not going to talk about that until the last month of the course. After you've selected which thread is going to go next, then you need to save the context, that is the state of the currently running thread, because you want to make sure that when that thread runs again, that it continues from the exact same point and in the exact same state that it left off in. Threads that are not running should never know that they got halted to let other threads go. They shouldn't be aware of this. So we are really going to save the contents of the current thread. And once we've saved the contents of the current thread, then we will load the contents of our new thread onto the CPU so that the new thread can continue its execution. But how we do that is very, very tricky. And there's actually two parts. So part one, let's open up a terminal here, and we're going to go into, not the include directory. So let's go into threads. So this is kern thread. And I'm going to open up thread.c. And I'm looking for a function called thread switch. Here it is, line 548 is the function thread switch. So what's going to happen is thread switch is the high level part of a context switch. And as part of this, it is going to figure out first what state the current running thread is. Like, did it call exit? Did it call yield? Did it block? It's going to figure out why is a context switch happening, and then it's going to figure out what kind of new thread am I going to run. So it's actually going to call the scheduler and get a new thread. And once it has selected a new thread, it is then going to call the low-level context switch. And the low-level context switch is what's actually here in the slides. And it's this assembly. So you have thread switch, which does the high level choosing of the next thread, and then it's going to call this function called switch frame switch, which is written in assembly to perform the low level context switch. Now, why do we need a high level context switch and a low level context switch? Well, the reason is the high level context switch is written in C. which means as per OS 161 and the compiler for its conventions for register use, it will only save and restore the caller save registers. It will not save any of the callee save registers, which means that we need to write a function in assembly specifically to save those other registers, the callee save registers. And that's exactly what switch frame switch does. Now, as per the question on Twitch, where do these register values get saved? They're being saved onto the threads stack. Now, the low-level context switch, switch frame switch, is going to be given two arguments. One is the address of the stack for the old thread, and the other one is the address of the stack for the new thread. So at this point, it already knows which thread is going to go next because it has to be able to complete the context store for the old thread, and then it's going to begin the restoration process for the new thread. So this slide here is talking about how we actually complete the context save. So we are going to make some space on the stack by moving the stack pointer. We are going to save the return address, the globals pointer, and then we save the callee save registers, which were not saved by thread switch. And then after we've done that, we save our stack pointer. And at this point right here at the end of the slide, it's not the end of the function, we have now completely saved the context of the old thread to the old thread's stack. The second part of switch frame switch is to begin the restoration process of the new thread's context. So then we're going to move from using the old thread stack to the new thread stack. And then because thread switch is only capable, as per the conventions of register use, of saving and restoring the caller save registers, we need switch frame switch to restore the callee save registers for our new thread. And that's actually what you see happening here. These are the callee save registers and the return address, and the stack pointers being restored, and by restored I mean loaded from the stack of the new thread onto the CPU. And then what we have is, you'll notice we are jumping to some address in the new thread to execute. Now, let's talk a little bit about some of this. I know CS350 might have been some time ago for many of you, and I know many of you probably forgot everything about 251 the second you wrote the last answer on your exam. Some operations in a pipelined computer take a little too long. For example, anything that interacts with memory is going to take more than a standard amount of cycles. So if you are using a pipelined architecture, which we are, it's entirely possible that if you load a value into a register from memory and then try to immediately use it, that the load won't actually have completed and you end up with garbage. So we have to make use of delay slots to make sure that longer running operations have a chance to complete before the next instruction in the pipeline has an opportunity to use it. Now in this case, what we've done is after loading the stack pointer, we insert the NOP instruction, which is an instruction that does nothing. And if you're sitting there staring at a blank wall, that's your brain going NOP, 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 NOP. Now, a couple comments on Twitch here. Isn't constantly switching between the different threads a costly operation? Yes, it is a costly operation. It's not free. And that's why there has to be a balance. If you switch too much, then you will spend more time performing the actual context switch than actually executing any of the thread's instructions. So you don't want to do the context switch too frequently. And at the same time, you don't want to do the context switch too infrequently, because then you are breaking the illusion of all the threads actually running at the same time. So it is a real balancing act. I can tell you on Solaris, which is an operating system that most of you have probably never touched, but its scheduling algorithm is actually quite similar to Windows and Mac OS's scheduling algorithm. They're all using multi-level feedback queues. The amount of time that threads are permitted to run is between, I think, 40 and 200 milliseconds. So, I mean, you can run a fair number of threads per second. And again, that comes down to OS. All right. And for those of you who didn't have a 251 exam, how lucky are you? I suppose that's one of the benefits of the shutdown, as many people didn't have to sit in fear in the pack. So another question here on Twitch is saying, does the CPU or something recognize when a thread attempts to yield and fails, continues, or does that thread's registers get saved and then immediately relocated? Okay, that's actually a really good question. So here's the thing. If you call thread yield, a thread yield is actually going to call thread switch, as we will see very shortly. And thread switch is going to call the scheduler to figure out what thread will get to go next. Now, an intelligent implementation of this mechanism will, if the scheduler says, hey, the thread that called yield is going to be the thread that runs again, then thread switch would be intelligent and not perform the context switch at all. Because again, saving and restoring yourself makes no sense whatsoever. So an intelligently implemented context switching mechanism would detect the fact that even though you've called yield and you are still going to run after the yield, it wouldn't actually do anything. That's not to say OS 161 was intelligently implemented in this regard. I believe it actually was, though. It's not that hard to do. Who detects the calls to thread yield? That's actually the kernel of the operating system. All right. So there are other, by the way, delay slots. So you'll see here we are restoring the return address register, and then we are jumping to the return address. And you'll notice here that we are putting something in the delay slot of the load again. And the jump instruction also has a delay slot. So we have something in that one. You could have technically put this add to pop the restored registers off the new threads stack where this NOP is, and then put this NOP in the delay slot of the jump, and that would have been equivalent, but this is how they decided to do it. So don't forget about delay slots. Now, if you're sitting there wondering, I've forgotten CS350, I've forgotten CS241, oh no, I forgot how to do MIPS assembly, we're not asking you to write any assembly code on the assignments whatsoever. And if you find yourself saying, hey, I need to edit the assembly code, no, don't do that, please. Because if you're going down that path, you have gone way down the garden path. You're all the way out at like Jupiter. Please don't touch the assembly code on the assignments. All right. So, as I said before, there are a number of reasons that context switches actually occur. And in fact, there are 4 primary reasons that we discuss. One of them is yield, and that is when we are voluntarily saying, hey, I want to give up the CPU. The thing to remember about yield is that it's not a guarantee. If you're the only thread, then calling yield will do absolutely nothing. I mean, it will actually call yield, but yield will be like, yeah, there's no other threads, so guess what? You're going to keep running. So yield is one way you could encounter a context switch. It's not a guarantee. Another way that you can get a context switch is when a thread calls exit, because when a thread is terminated, we want to keep the CPU at 100% utilization. So we want to actually choose another thread. And for those of you saying that CS251 has moved to ARM, why haven't we moved to ARM? We are moving away from MIPS. I'm not sure exactly when it's happening. The discussion was to move this course towards ARM, but now I'm moving, or at least I'm thinking, you know what, why don't we just do x86? That's my thoughts. We'll see. All right, 2 other reasons why context switches actually occur. So a thread can block. So imagine it this way. Suppose you are trying to write some kind of video game like King's Quest. King's Quest was super popular in the 90s. If you haven't played King's Quest, get a DOS emulator and try King's Quest 5. It's a really popular game. And the idea is you kind of like point and click to explore the world, type some commands in. That game doesn't do anything unless you actually interact with it, which means that thread is waiting for you to do something. Well, if the thread is waiting for you to do something, is it sitting there idling on the CPU? That makes no sense. So threads that are waiting for some event to happen have a state known as a blocked state. And we'll talk more about this later, but a thread that is blocked waiting for something is not running or ready. And when your thread moves from running to blocked, we need a context switch to make sure that the CPU maintains its utilization. The fourth reason why we can get a context switch is something called preemption. And preemption is when a thread is involuntarily kicked off the CPU, which is actually how we implement concurrency today. And we'll talk more about that later. Someone on Twitch says you can actually play King's Quest 5 in a browser. I recommend you go try it before assignments get too crazy. All right, so you can take all these thread states and actually create this lovely thread state diagram, and it kind of shows you how threads move between the different states. So a new thread will get plopped into the ready pool. The threads from the ready pool can only go to a running state if the scheduler says, hey, it's time for you to run. Threads that are running can go to 3 different states. They can be preempted, that is involuntarily kicked off the CPU, or they can call yield to voluntarily give off the CPU. And whether you are preempted or whether you yield, you will go from running to ready because you're not waiting on anything. You didn't really want to give up the CPU. If you are running and you call exit, you're dead, so you go out into the ether. And then if you are running and you realize that there's some resource that you don't have and you need to continue, then you go to this blocked state. And threads that are blocked do not go directly to running when that resource becomes available. They will go to the ready state. And again, that will come into play next in our next episode when we actually start to talk about synchronization. So 3 states of a thread we really care about are ready, running, and blocked. Now, one of the things we like to do in this course is ask you to draw what the stack would look like under certain circumstances. So this is an example of a stack for a thread that voluntarily created a context switch by calling, of course, thread yield. So what we have is all of our other stack frames. So this would be, I don't know, maybe it was adding some numbers together, or maybe it was trying to figure out what thing you clicked on the screen. And then you called thread yield. So then we have thread yield on the stack. Thread yield calls thread switch, and thread switch is going to call switch frame. So this is what our stack would look like. Now, here's the thing. How are we going to implement this concept of time sharing? Because threads don't want to give up the CPU. Now, back in the day, so in the 80s and 90s, but mostly the late 80s and throughout the 90s, Mac OS and Windows didn't actually implement true time sharing. How they implemented concurrency was this thing called cooperative concurrency. Cooperative concurrency means it's friendly. It relies on both the developer voluntarily giving up the CPU in order to have any concurrency actually happening, which means that if you wanted to make multiple things share the CPU, you had to put thread yields in your code. Your code had to have the threads actually call exit, and your thread had to block. And if your thread did not do any of those 3 things, then it wouldn't share the CPU at all. And yes, both Windows and Mac OS used cooperative concurrency up until about the year 2000. So they actually used it for a really long time. That doesn't give us the best CPU utilization, and it also doesn't give us the best user experience. Now, it worked in the late 80s and the 90s because our hardware wasn't good enough to really show off the ability of running multiple things at the same time. And the mentality of people using computing resources in that time wasn't, hey, I need to have 6 YouTubes open, because the internet was still a pretty new thing to most people, and YouTube wasn't really a thing either. I mean, even today, you probably shouldn't run 6 YouTubes at the same time because it's kind of weird. I mean, you can do it if you want. So if we don't want to do cooperative concurrency, if we actually want to enforce the time sharing, and we don't want the developer to have to manually call thread yield every 40 milliseconds, but how would they even know that it was 40 milliseconds had elapsed? We need some way of involuntarily kicking the thread off the CPU. We need this concept of preemption. We need a way to kick that long running thread off the CPU so somebody else can have a turn. Okay. So a couple bits of terminology here. We talk about this concept of a scheduling quantum. So with time sharing, we want to impose a limit on how much time each thread is permitted to run on the CPU for whatever turn it's on. So the scheduling quantum is that limit. So it's the upper bound on how long a thread is permitted to use the CPU for in any turn that that thread gets. And the scheduling quantum has to be decided by the operating system developer in their and it's related to the hardware. It's quite complicated to figure out what is an appropriate scheduling quantum. But as I said, Solaris, its scheduling quantums were between about 200 milliseconds and 40 milliseconds. And I imagine Windows's are roughly the same. So that's the upper bound for how long a thread is going to be able to run for. But how do you stop a thread from running? So you have one CPU with one core that can only run one thread. And that one thread is ray tracing, which means that it's just doing math and it's not doing I/O operations. It's not blocking, it's not yielding, it's not doing anything else. So how does the operating system wrestle control away from that thread to another if the operating system would need to execute instructions in order to do so? How can you actually get control away? It's an answer. Interrupts, which means hardware. So remember, you have hardware devices. So for me, the hardware devices I have on my desk that I can actually pick up, I have, of course, for my writing purposes, I have one of these Wacom tablets with the pen devices so that I can write notes. And there are various buttons. Anytime I touch down on the area of the tablet, anytime I push a button on the pen, that actually sends a signal from this piece of hardware to my computer. And that signal is typically referred to as an interrupt. When you push a key on your keyboard, that fires an interrupt. It sends an electrical signal from the keyboard to the CPU. When the CPU receives that electrical signal, the CPU is like, okay, I have received this signal. What do I do now? And the truth is the CPU doesn't actually care about who fired that signal, or it doesn't even know what to do with it, because it's the operating system, it's the kernel's responsibility to actually respond to these electrical interrupts. It's the kernel's responsibility to handle interrupts and to interact with the devices. So when the CPU receives an interrupt, the CPU is going to cease executing whatever it was executing, and it's going to start executing the interrupt handler for the operating system. Now, how does the CPU know where the interrupt handler is for the kernel? Because the CPU has some special memory on it. And one of the special things that it knows about is this thing called a trap table. And in a trap table will be the addresses of the exception and interrupt handlers for the kernel, so that when the CPU receives an interrupt, it knows the program counter for the kernel's interrupt handler. And when the CPU receives an exception, it knows the address of the kernel's exception handler. So when we get that electrical signal, the interrupt on the CPU, we are going to stop executing our current thread, and we are going to start immediately executing the interrupt handler in the kernel. Now, of course, this is going to cause an interesting problem, because I'm going from executing my thread and it's got all of its values stored in the registers, and now I want to go execute the kernel, which is going to want to store values in those same registers. So you're thinking, well, isn't that going to clobber everything that's on the CPU, that context? And the answer is yes, it would. Except the very first thing that the interrupt handler does in the kernel, and we will be looking into this in greater detail later in the course, the first thing that the interrupt handler actually does is it saves the complete context, which means every single register, to the current thread's stack before it starts actually executing the true interrupt handler to figure out what device has fired the interrupt and what should I do with it. So the very first thing our interrupt handler does is it saves the state, and then it actually calls the interrupt handler. And then, of course, after the interrupt has been handled, we will return to the interrupt handler to restore the state of the thread that was running, that was interrupted by the key being pushed. So a question on Twitch. So there's a couple questions here. The first question is, so is the exception handler always held in memory, or is it fetched and cached from disk like any other program? That's a very interesting question. It comes down to implementation details of the operating system and architectural details. For OS 161, everything is in memory all the time, so we don't actually do fetches from disk like we would do with a modern operating system. I've never actually looked at the internal, this particular part of the Linux kernel, so I can't say for certain, but I think that these exception handlers are in memory all the time, and that is unusual for most things, because one of the problems with keeping programs loaded 100% of the time is that you are going to run out of physical memory at some point. So what we actually tend to do is on-demand loading. Of course, with an exception or interrupt handler, we want to make sure that they always live at the same address every time. And so, at least in OS 161, that means that we're just going to keep it in memory the whole time. We'll talk more about that when we talk about virtual memory. For now, just assume that everybody does keep the exception and interrupts handlers in the same place in memory constantly, and it's not something we're going to load on demand. The other question here is, would an exception like division by zero have an entry in the trap table? So again, this comes down to architectural implementations, the actual hardware and the operating system's implementation. In OS 161, because it runs on MIPS actually doesn't differentiate between interrupts and exceptions. Everything is an exception in MIPS, and an interrupt is just a special kind of exception, and there are many different kinds of exceptions. So on our MIPS system, our trap table actually only contains a single entry to a singular exception handler. But on something like an Intel CPU, interrupts and exceptions would probably be handled by different things, and they would be differentiated. Again, comes down to hardware. All right. So this is actually how we are going to wrestle control away from our thread. Now, if we were looking at the stack after an interrupt, so our thread was happily chewing along, la 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 la, here's what I'm doing. I'm gonna, multiply some matrices together, and then bam, somebody pushes a key. That interrupt is going to immediately stop the execution of me multiplying matrices. I should apologize in advance. Most of my examples are going to relate to graphics, given that I am a graphics researcher. The second the interrupt is fired, the CPU is going to switch to executing the interrupt handler. The first thing the interrupt handler does is it produces what's known as a trap frame. A trap frame is going to store the value of every register. And that means the callees save registers, the callers save registers, and all of the special ones like low and high. It saves everything. Now, why does the trap frame have to save everything when the switch frame only has to save some things? Well, the switch frame is actually called by a piece of code, and it was called voluntarily. Either you called it by calling thread yield, or the kernel called it for some other reason. So it's going to obey then, or need to obey, those register save and restore conventions. When an interrupt is fired, we're going to begin executing a function, but it wasn't our choice. We, the program running, didn't call it, and the kernel didn't call it either. The CPU was interrupted. It's normal. Think of it as an emergency broadcasting system. We interrupt your regularly scheduled programming to let you know that a certain unnamed individual thinks that we should nuke hurricanes. I wish I was joking, but somebody has said that in the last 6 months. We had no control over that. The network had no control over that. So all of those register, save, and restore conventions are not in play here. So the trap frame has to save everything. And then after we've saved everything, then we'll actually do the body of the interrupt handler. Now, how are we going to fire an interrupt? How are we going to do preemptive scheduling? How are we going to force? We know that in order to preempt the thread, we need to fire an interrupt. And in order to make sure that the thread is being, that this is fair, we need to make sure that the thread that is running gets interrupted after a certain period of time, and that certain period of time should be the scheduling quantum, that upper bound on how long the thread is permitted to run. So who's going to fire this interrupt to preempt the thread? The answer is your clock. Every computer has a clock device, and it is actually a device, and you can actually interact with the clock in the kernel. You can set timers to go off. So in particular, I can create a timer on the clock to go off every 40 milliseconds. And when the clock timer goes off, that is when the countdown on the clock reaches 0, the clock will be like, hey, I'm done, and it will fire an interrupt because it doesn't know what to do next. And the interrupt, when it goes off, will cause the CPU to go from running your code to saving the state of your code and then running the interrupt handler for the clock device. And then when it goes in there, it'll be like, oh, the quantum has expired. We need to do a context switch away from the current thread to a new thread. So that's how we're going to implement preemption and do time sharing. So let's actually take a look at what the thread stack looks like for preemption. So our thread was happily chewing along here, firing some rays into the world and trying to figure out, do they intersect this sphere? Do they intersect that sphere? Or this triangle? I'm not crazy, really. Okay, maybe I am. And then bam, our quantum expires, so our timer interrupt goes off because the clock has counted down to 0. Timer interrupt. So the CPU is going to stop executing your code, and it's going to save the trap frame, which is the state of what you were doing prior to the timer interrupt. So all of those registers are now saved on your stack. And now we're going to call the interrupt handler. The interrupt handler will realize, okay, this was an interrupt, and it was the clock, so we'll call the clock's interrupt handler, and the clock's interrupt handler is going to be like, oh, the scheduling quantum has expired. I better call thread yield on your behalf, because I want you to try to give up the CPU. So we call thread yield. Not we, the kernel calls thread yield on behalf of the thread that was running. And thread yield calls thread switch. Inside of thread switch says, oh yes, indeed, there are other threads which could run. let us choose one of them to go next. And so then thread switch calls switch frame. And the context switch is completed. Now, a lot of people ask me, are we double saving? Like, we save the trap frame here, and then we're going to save those registers again here? Isn't this saving the same values here as we're saving down here? No. The trap frame is saving the state of what you were doing. The switch frame is saving the state of what came in between the interrupt and then the actual context switch. It's saving the mechanism to switch back at a later time. So the trap frame and the switch frame, they're not saving the same things. And I will post a guide that discusses this in greater detail to Piazza. So what I'd like to do now is actually go through an example of two threads sharing the CPU with preemptive concurrency. Now we have thread 1, which is our greedy little thread, and it never wants to give up the CPU. And we have thread 2, which is our super friendly thread, which calls thread yield all the time. And in our start state, what we actually have is we have thread 1 is actually running, and thread 2 has previously run, but also previously given up the CPU voluntarily. So thread 1 is running, and because it never calls yield, it never blocks, and it never terminates, the quantum is going to expire, which means we're going to get a timer interrupt. Now on that timer interrupt, we get the trap frame to save the state of thread 1. That calls the interrupt handler. The interrupt handler realizes, oh, the quantum has expired, I need to do a context switch. So we call thread yield, which calls thread switch. And then thread switch calls switch frame. Now, switch frame is an interesting function because it's going to do the low-level context switch, which means it's going to save the callee save registers for thread 1, but switch frame from thread 1 is also going to load the callee save registers for the new thread and then pop the switch frame off the stack of the new thread before returning to the return address, which is thread switch in the new thread. So it looks like that. Thread switch is going to return and then to thread yield, and then thread yield is going to return, and then thread 2 finally goes back to running. Now, thread 2 I said is the friendly thread, and it's friendly because it calls yield before its quantum expires. So it called yield, yield called switch, switch called switch frame, which again is going to do the low-level callee save store and then callee restore for the new thread. We go back to the rude thread that doesn't like to share, and now its switch frame, its callee save registers have been restored. We jump to the return address, which is going to be the return point for thread switch, which is going to restore the caller save registers. That returns to yield. We return to the interrupt handler, which is just going to return immediately because we're done. We were long since done handling that. And then the trap frame, which will restore the actual thread state, and then we'll go back to running there. So another question on Twitch here is, does switch frame always work with the same core? If so, how do we ever start working with more than one core? So yes, it can work with more than one core. So what's going to happen is when we have a context switch, it's typically happening at the core level. So you're not going to, on a context switch, have a thread coming off core 0 and then be putting a thread onto core 2. So it's going to be the thread is leaving core 0 and we're going to be putting a new thread onto core 0 because we're trying to keep that core's utilization at close to as 100% as possible. So you're not going to be taking something from one core and putting something onto a different core on a context switch. And what you're actually going to have is it's entirely possible that on a multi-core system that you actually have multiple context switches happening simultaneously. That can actually happen. And we'll talk about how you handle scheduling with multi-core systems when we talk about scheduling later on. All right. So a couple interesting things to note. One of them is that if you give up the CPU because you either yield or blocked before the scheduling quantum has expired, the next thread that runs doesn't get to use your leftovers. And the next time you run, you won't be using your leftovers either. Each time a thread moves from ready to running, the scheduling quantum starts new every time. And if you terminate early, then the next thread that runs will start a brand new quantum. So there's no concept of saving leftovers from one thread for another. So don't worry about things like that. The other thing I want you to remember is that each thread is going to have its own stack, as we've kind of shown in these diagrams here. So we're going to save your context on your stack and your neighbor's context on their stack. So you're not going to have any of another thread's context stored on your stack. We're going to keep those separate, which makes sense. All right. Now, one thing I'd like to show you then before we go is another sample problem. This sample problem here is called 2 threads. So what we have is a little bit of pseudo code here that's going to be executed by 2 threads. Thread 0, just to keep in mind, is always going to go first. And we're going to assume this is a single CPU system that can only run one thread at a time. So we're going to use preemptive time sharing here. So we have 2 threads that are running this code here. So for I equals 1 to n, we're going to do some computation for c milliseconds, followed by a sleep for s milliseconds. The sleep, by the way, is a blocking operation. You are not ready, you are not running, you are blocked until your timer expires. And then we're going to repeat this cycle n times. And then what we're asking you to do is, given some relationships between the length of the computation, the length of the sleep, and the scheduling quantum, we want to know at what point in time do both threads finish. Now there's 2 parts here. Take a look at this problem and give it a try before Thursday's episode where we'll take this up. Now, a couple hints I want to give you. While you are blocked, that is, while you are asleep, the scheduling quantum for you doesn't matter because you're not using the CPU. The only time where the scheduling quantum matters is when you're actively using the CPU. If you aren't using the CPU, I don't care. You can sleep for 6 days if you want. Doesn't matter because you're not using CPU resources and you're not blocking against others using them either. So the sleep time and the scheduling quantum are completely you're not going to get a sleeping thread preempted because the sleeping thread isn't running. So just keep that in mind here. All right. So that is actually the end of our introduction to threads. And I know it's a very, very brief introduction. For those of you looking to get some more experience, I really, really recommend you play with the POSIX threads, pthreads library, and OpenMP. Try to create some threads, find a simple problem, and like image manipulation, make all the pixels double the red component. Do that using multiple threads, and then compare how long it takes to do that with multiple threads versus just a single one. But it'll give you a sense of how do I use threads in the real world and how do they actually behave. Now, in our next episode, we are going to start talking about synchronization, because now that we've given you the ability to run multiple things at the same time, or at least give you the illusion of multiple things running at the same time, we kind of created a teeny tiny problem here. And just to give you a preview of that, think about this. The timer can expire at any point. And if you are trying to save something to, let's say you're trying to add 1 to a variable, what if you add 1 to a variable, but the preemption, the context switch happens before you were able to update that variable in memory, and then another thread tries to use it? Think about that. This is a problem we've created with concurrency, and in our synchronization module, we're going to give you the tools to fix the problem. So we will see you on Thursday for episode 4.
Hello, I'm a Mac.
And I'm a PC.
Are you going in for a checkup?
Well, I'm upgrading to Vista today, which is great, but I get a little nervous when they mess around with my insides.
Well, what do you mean? Isn't it just straightforward?
Not really. Like a lot of PCs, I have to update my graphics card, my memory. If I want the premium package, I need a faster processors. It's major surgery.
I'm sorry about that.
Listen, Mac, if I don't come back, I want you to have my peripherals.
Oh, come on. PC, you're not gonna... Ah, speaking of peripherals...